Welcome back to Bionics of Surfaces. We're going to look at some drops of water on surfaces now. This is polypropylene probably. So a drop of water on it will sit up, contact angle of about 50 degrees, maybe 60 degrees. So here we see putting a small drop of water on there. Just get in focus. I think it gets a little bit better a little bit later on. It's not quite close enough, so let's zoom in a bit more. So here we are a little bit closer. We can see the drop from the side, if I can get it at the right angle, and we can see if I tilt it up that the angles change. The drop tries to move forwards, but it's pinned to start with until it's deep enough that it can slide down. I think I have to have some more water. I'll give it a little shake to get it to move, but it is stuck to the surface by the difference in contact angles between the advancing and receding angle. Now it's a bigger drop of water, it will slide down much better, and you can see there's a big difference between the angle on the right at the bottom and the angle on the left at the top. Now it's kind of sliding. The angle at the back is nearly zero and the angle at the front is over 90 degrees. Now we have a drop of water on a piece of normal glass. You can see that the angle is very much like it is on the polymer, and it behaves similarly, although the angle at the back is lower, and it's rolling about quite well. That's because this piece of glass is a little bit dirty. This is what happens on a clean piece of glass. You can see then that the water will spread quite well, and particularly at the back it will go down to 0 degrees. You can see, look, it's spreading out. It's quite difficult to keep it as a drop. It's not perfectly clean. You can see it's spreading, so it's lifting up at the front, but you can see it leaves a lot of water on the surface and doesn't actually shake off completely at all. Here's another go, I think. There it is on the surface, spreading out to quite a low angle, and spreading out to 0 pretty much on the back. That's because obviously the glass has a high surface energy. It's very hydrophilic. Moving on to rough surfaces, if we take a piece of paper, in this case a tissue, obviously it will absorb water eventually, but if we put a drop of water onto it carefully, we can see that it sits, so here it is, we can see that it sits first of all as a drop, neatly piled up on this tissue. It's just a perfectly normal lab tissue. It takes a while to get to the crack between two fibers because it's hanging, as we had in that paper, underneath the fibers. Although they're hydrophilic, the water can sit in between the fibers and doesn't actually run through because the surface tension is stopping it. Eventually the fibers get wet and it penetrates inside by capillary tension. Here is some shoe water repellent that I'm going to spray on one of those pieces of paper, and we will come back and see it again. This time we would expect it to be water repellent and rough because it's still got the paper structure. This paper towels have no filler, so they're quite fibrous. Here it is against the slide to hold it flat. And here comes a water drop. It's taking a bit of time, sorry about this. There it is sitting on there. You can see it's not very mobile because there's a lot of contact between the water drop and the surface, and particularly between the edge of the water drop and the surface. But so there I am trying to move it, but it isn't wetting the paper at all. There are also the little dimples in the paper that also tend to catch it. I think we'll stop here and go to the next thing. Now finally we have a superhydrophobic surface with soot, in this case, on glass. It's somewhat unstable, but we will see when I get a better one that the water drop bounces off the surface, and in this case it falls towards the back. It depends on how you hold it. It's very difficult to hold it flat enough because a couple of degrees will make the water drop fall off because it's stuck barely at all. The difference between the advancing and receding angles is almost zero. So where is it? I'm hoping it's coming up. So here I am adding a drop to this sooty surface, and it will roll off the back. I think I'll play it again. I think I'll slow it down at that point so it'll suddenly go quiet for that time. Oops. So here it is at 10 times slowed down. You can see the drops of water bouncing off my sooty glass surface, unless they manage to get trapped underneath the soot and stick to the glass. Here they are bouncing along. What you can see is another effect coming in, that the soot is spreading over the surface. We'll look at that more closely in a moment, but for the moment we're looking at the drops of water bouncing and flying off. And for my last demonstration today, some sand that's been treated to make it water repellent, collecting on the tops of drops, so spreading up the drop to make what's called a liquid marble, or what's known as a liquid marble, let's say, put it like that. Here we go. It either spreads up very quickly like that, or sometimes it sits at the bottom. It depends how much the drop wobbles when it is applied. So here's me putting one on more carefully, and it doesn't go quite so high. There isn't so much sand on the top of that one. You can see water at the top that's got no sand on it. On the other one is completely covered. If we wobble them around, we can make them roll off the surface here. Can actually sometimes get them to go onto the surface of a beaker of water, but that's really difficult. I haven't managed to get it to work recently. So there I've made two go together and form a bigger drop, and if you roll it around it'll stay as a drop and then fall off. So that will do. Some effects of surface tension demonstrated here relatively simply with simple equipment.